Let us discuss the different order relations. The order relations include less than, greater than, less than or equal to, and greater than or equal to. The first two are referred to as the strict inequalities, while the other two are the non-strict inequalities. Alright. On the number line, positive infinity to the right and negative infinity to the left. If we have two numbers, say A and B, we say that A is less than B. So if a number appears to the left of another number, just like this one, A is located to the left of B, we say that A is less than B. This is equivalent to B greater than A. If a number B is located to the right of the number A, then we say that B is greater than A. We write down the definition of less than and greater than. So let A and B be real numbers. A is less than B, written as A less than B if and only if B minus A is positive. So we can also say that A is less than or equal to B if and only if B minus A is positive or A is equal to B. Alright? Let A and B be real numbers. We say that A is greater than B, written as A greater than B, if and only if A minus B is positive. Alright. So 3 is less than 7, since 7 minus 3 is equal to 4, and 4 is positive. Alright? Negative 4 is greater than negative 9, since negative 4 minus negative 9 is negative 4 plus 9 equal to 5 is positive. Alright? Is 2 less than negative 4? Let us see. If 2 is less than negative 4 minus 2 is negative 6, and negative 6 is negative. So, it is not true that 2 is less than negative 4, because the requirement for less than is that when you subtract 2 from negative 4, it must be positive. But in this case, we have shown that it is negative. So therefore, that relation does not exist. Let us now list down some important theorems about order relations. The first one is, if A is less than B and B is less than C, then A is less than C. Okay, so for each of these theorems, following theorems, we say that A, B, C, and D are all real numbers. So if A is less than B and B is less than C, then A is less than C. So negative 4 is less than 0, and 0 is less than 5. So that means that negative 4 is less than 5. So on the number line, we can show the relation negative 4 and 5. Since negative 4 is to the left of 5, then it is true that negative 4 is less than 5. Okay? We can also indicate the 0 here. Negative 4 is less than 0, and 0 is less than 5, so negative 4 is less than 5. Next, if A is less than B, then adding any constant C to both sides of the inequality will not change the sense of the inequality. So 3 is less than 6. Add negative 2 to both sides. And what do we get? 3, negative 2, 6, negative 2. 3 minus 2 is 1, 6 minus 2 is 4. Still, 1 is less than 4. So adding any constant to both sides of the inequality will not change the sense of the inequality. If A is less than B and C is less than D, then A plus C is less than B plus D. If we have two inequalities, the same inequalities, both less than, for example, 1 is less than 3 and negative 4 is less than negative 1. If we are going to add corresponding sides, 1 and negative 4, 3 and negative 1, we'll be getting negative 3 and positive 2, and we know that negative 3 is less than 2. Alright? So, if we have two inequalities with the same sense, both less than, then adding corresponding sides will retain the sense of the inequality. Alright. We now go to the fourth one. If A is less than B and C is greater than 0, then AC is less than BC. So if we multiply both sides of the inequality by a number C that is greater than 0, meaning to say that C is positive. So if we multiply both sides of an inequality by a positive number, you retain the sense of the inequality. Example, 2 is less than 9. Multiply both sides by 3. So we have 2 times 3, 9 times 3. 2 times 3 is 6, 9 times 3 is 27, and 6 is less than 27. So we retain the sense of the inequality. If it is less than, it remains as less than, provided that our multiplier is a positive number. The next one is important. If A is less than B and C is less than 0, meaning to say C is negative, then AC is greater than BC. So take note, the original inequality is less than. We multiply both sides by a negative number. You have to reverse the sense of the inequality. 4 is less than 7. Let us multiply both sides by negative 3. 4 times negative 3, 7 times negative 3. 4 times negative 3 is negative 12. 7 times negative 3 is negative 21. On the number line, negative 12 and negative 21. Negative 12 is to the right of negative 21. So that means that negative 12 is greater than negative 21. So we see that from the original inequality of less than, it becomes greater than. So the moment you multiply both sides of an inequality by a negative number, make sure that you reverse the sense of the inequality. Alright? So we mark this as an important theorem. If we multiply both sides of an inequality by a negative number, make sure that you reverse the sense of the inequality. But if you are to multiply both sides of an inequality by a positive number, you retain the original sense of the inequality. When you add a number to both sides of an inequality, be it a positive or a negative number, you need not change the sense of the inequality. Alright? Let us now discuss the different intervals. But before that, we also have, let me give you an example of a continued inequality. An example of a continued inequality is x between 5 and 13. This is equivalent to the inequalities x greater than 5 and x less than 13. Alright? This continued inequality is equivalent to the intersection of these two inequalities, x greater than 5 and at the same time x is less than 13. So let us locate the numbers 5 and 13 on the number line. So for the continued inequality x between 5 and 13, it refers to all numbers, all numbers between 5 and 13. X is greater than 5 refers to this set of numbers, while x less than 13 refers to all these numbers. And since the connector is AND, it refers to all numbers between 5 and 13. Alright? But there is no continued inequality for say for example, x is less than 3 and x is greater than 5. So let us draw a number line and let us indicate the numbers 3 and 5. X less than 3. X less than 3 refers to these numbers, while x greater than 5 refers to all these numbers. And see that there is no intersection between these two sets of numbers. So therefore, you cannot write this as a continued inequality. Alright? We cannot write this as a continued inequality. We cannot write this as x greater than 5. Alright? And what? Let me see. Yeah, there's no way we can combine these two. No? We cannot write this as what? As one continued inequality. Simply because there is no intersection. No? There's no way we can write this as this one, x less than 3. It is true that x is less than 3 and x is greater than 5. But you see here that 3 is greater than 5, and that is absurd. Right? So we cannot write these two inequalities as a single inequality. Okay. Before the intervals, let me give you one example involving inequalities. Say we have set A, the set of all x's, such that x is between 2 and 10. And then set B is the set of all x's, such that x is less than 4. Alright? What will be the union of A and B and the intersection of A and B? Both A and B are sets of numbers, real numbers, not just integers. It is not specified here that x is an integer or a natural number. So it is understood that x is a real number. So between these two sets of real numbers, let us identify the union of sets A and B. Union means we combine. We combine all elements of A and B. Let us illustrate. For set A, it will be the numbers between 2 and 10. Right? While for B, it will be all numbers less than 4. Okay? And set A and set B. If we are to combine, how do we write the elements of A union B? All elements of A together with all elements of B. So it is quite obvious that the union will be the set of all x's such that x is less than 10. Do you see that? Numbers less than 10. Beyond 2 to the left, those numbers are contained in set B. Though set A consists only of numbers between 2 and 10, but since we are to add the elements or the numbers in set B, which are all less than 4, combining the two will be getting a set of numbers that where each element is less than 10. Alright? How about the intersection? We identify the numbers in A that can be found in B. And it is quite obvious that these numbers start from 4, or it starts from 2 rather, and ends at 4. So the intersection of sets A and B will be the set of all x's such that x is between 2 and 4. Okay. Let us now discuss the different intervals. Inequalities can be expressed in terms of intervals. The first one is the open interval denoted by A, B between a pair of parentheses. we define the open interval AB as the set of all x's such that x is between A and B. Okay, you should not mistake this pair of numbers to the pair of numbers xy in the Cartesian plane r squared. No? So this is different. This is different from the open interval AB. The open interval consists of real numbers. Real numbers. So when you see a pair of parentheses and the numbers a comma b, it refers to, or the set refers to, all numbers between a and b. And let us illustrate that. In the number line, we have the numbers a and b. So all numbers in between, we have to exclude the endpoints. No? So we use a hollow circle, an open circle there. So all numbers between a and b except the endpoints. That is the open interval. Another way of illustrating the open interval AB is by using a pair of brackets, or rather parentheses. No? So from A to B, including the numbers in between. Alright? That is the open interval. So example is the open interval 5 and 8. So we illustrate this on the number line. From 5 to 8 there. Or you can use a pair of parentheses. And that is equivalent to the continued inequality x between 5 and 8. So this continued inequality, or this set, can be written in interval form using a pair of parentheses 5, 8. Alright? These two are identical. They both refer to the same set of numbers. No? Numbers between 5 and 8 exclusive of the endpoints. If we are to include the endpoints, then that will be a closed interval. Closed interval. We denote the closed interval by a pair of brackets, A and B. So we define the closed interval AB as the set of all x's such that x is between A and B, including the endpoints. So see the difference? In the open interval, the endpoints are excluded. But in here, the endpoints are included. So let us illustrate that. A and B, including the endpoints. So it must be a closed circle together with all numbers in between. Or you can use a pair of brackets together with all the numbers in between. So if we are to indicate some numbers here, -3 and 0, we write the interval as open bracket -3, 0, close bracket. So it is called a closed interval. Right? Next, we have half open intervals. The first one is interval. Let me just write here half open on the right. Half open on the right. So how do we indicate that? Or how do we indicate that? Half open on the right, so it must be closed at the left. Close at the left, open at the right. And what is the definition? The set of all x's such that x is still between a and b, including the left endpoint. Including the left endpoint. So here is A and B. Close at A, but open at B. Or open bracket at A, close parenthesis at B. Next, half open on the left. So it must be open at A but close at B. It is the set of all x's such that x is still between A and B, including the right endpoint. So we illustrate. Open at A but close at B. Open parenthesis, close bracket, and all points in between. No? You can either use brackets and parentheses or open close circles. No? You can use any of the two. You don't use both, just one. Choose one. No? Either an open circle or a close open circle and a closed circle for open and close endpoints, or open close parentheses or open close bracket. Alright? So half open on the right is the same as half close on the left. No? Half open on the left is the same as half close on the right. So we have other intervals. We have A to positive infinity. So it will be the set of all x's such that x is greater than A. Or close at A to positive infinity, the set of all x's such that x is greater than or equal to A. Negative infinity to A, set of all x's such that x is less than A, and negative infinity to A, close at A, the set of all x's such that x is less than or equal to A. Alright? So how do we illustrate this? So A, and A. X greater than A, meaning to say numbers to the right of A open. So open at A to the right, indicate positive infinity. X greater than or equal to A, all numbers to the right of A including A, so close at A to positive infinity. X less than A, all numbers to the left of A and open at A, so negative infinity. Now, please take note, for letter C, you do not write A to negative infinity. That will be wrong. You always start with the lower number at the left and the higher endpoint number at the right. So you should not interchange the endpoints. And finally, x less than or equal to A. So that means all numbers to the left of A, including A. So from negative infinity to A. Alright?